Hey, we are now starting topic 14 for IB Physics, higher level, with digital technology. And you can remember that as dig it, all the technology. What we're going to do is we're going to look at some simple problems on binary numbers. We're going to look at how these almost outdated things called CDs work with interference of light. And we're going to do a calculation on the little tiny pits within those CDs. In our decimal system of counting, we have a number like this, 8,369, and the columns mean different things. This column will mean 9 ones, this will mean 6 tens, 3 100s, and 8 1000s. That's obvious. However, I was talking to my friend, a robot, and he said he had trouble counting that way because he's going to count with switches that are either on or off. They don't have 10 different positions they can be in. So if you have only an on or an off, you can think of that as a 0 or a 1. And the columns in a binary system are going to be represented by these things. 2 to the 0 power can be a 1. 2 to the first, this can be a 2, this can be a 4, an 8, 16, a 32, 64, or 128. So let's say that you have a binary number that is 0, 0, 0, 0, 0, 1, 0, 0. That means you have 0 ones, 0 twos, but you have a 4. So in decimal, you would say that is the number 4. So let's say I give you the number 0, 1, 0, 1, 0. Take a minute, pause it, see if you can figure out what that is. What that's saying is you've got 0 ones here. You've got a 2 though, because this is the 2 column. You have 0 fours, but you do have an 8, because this is the 8 column. And then these don't do anything. You don't have anything. So this would be the number 10. Converting from decimal to binary, I think is a little bit harder. So let's say you want to convert the number 6. You start with the largest column you can use and say, I'm going to need a 4. So that's a 1. Then I also need the next column, a 2. That's going to be a column. And do I need a 1? I don't. So that is my number right there in binary. 95 is a little bit more complex. Biggest column I need is, I do need a 64. So I get a 1. Do I need a 32? No. Do I need a 16? Yes, I do. And that's going to give me a total of 80. You got to keep a running count here. Do I need an 8? Yes, it's going to give me an 88. Do I need a 4? Yes, gives me a 92. Do I need a 2? Yes, it gives me a 94. Do I need a 1? Yes, that's going to give me 95. And so then my number in binary is this here. A type of digital storage that's not too difficult to understand and that you're probably somewhat familiar with is a CD or a DVD. And there are tiny, tiny grooves on that in a spiral pattern that contain zeros and ones that can be turned into all types of information. And those tracks have been hit with these things called pits and lands. And as your CD spins, beneath it will be a laser beam. And that laser beam is firing a laser up at the bottom and also receiving what bounces off. It's going up and going boing and coming back. And if it comes back and it receives no craziness, it's going to have constructive interference. When you have a difference in path length between, let's say, the left part of the laser and the right part of the laser of 0, and that's going to be no interference, and it's going to register that as a 0. However, let's say part of it bounces off here and part of it bounces off here. Now they've traveled different path lengths. And if your difference in path length happens to equal half a wavelength, you get destructive interference. And that laser receiver is going to say, oh, I'm going to call that something different. I'm going to call that a 1 in binary. And you may ask then, how big does this need to be to cause that nice destructive interference? Well, you know you need half a wavelength of path difference. So if this height is a quarter wavelength, let me make that again, a quarter wavelength, and it goes a quarter wavelength extra and another quarter wavelength extra. That gives you your half wavelength, which leads to a 1 that your CD or your DVD player will sense. So let's say the laser on your CD reading device has this wavelength of 530. You should be able to calculate how deep that pit should be to provide that destructive interference that you need. And so the simple equation we had was that 1/4 wavelength will give you that destructive interference after it bounces there, and that equals our pit depth. And so then you can just plug in your numbers, and 1/4 of 530 nanometers is going to give you your answer of about, when you round it, 130 nanometers. That's a pretty small way of storing some information.